like Emmanuel said, I'll talk about spatial modeling for building agricultural resilience in Africa. This is my formal topic for the presentation, but I also have an informal topic, which is basically what is the role of spatial modeling in agricultural advisory for climate change resilience. So there's the formal and the informal topic, basically, which they speak to each other, but I'm more interested in the informal one because it talks about the problems or the issues that I want to address in this presentation. So in my current work, basically we have what we call the impact and adaptation chain, where we believe that climate change investment planning, it should be risk informed and should also be science based. So we have to know the risks of climate change, and based on that risk, we should plan for it. So we have this adaptation chain where we look at the climate, which is the first time, and then we look at water availability, we look at the effect on crops. At the same time, we then go the other side on the action part, where we then say, okay, given these effects, what is it that we can do basically to build adaptation, and what are the economic implications of each of the adaptation actions? So we look at the impact. At the same time, we also cross and look at the actions. But in this whole discussion, we also focus on uncertainty, because we also have to communicate very well the uncertainty in the modeling process. So when we talk about approaches to agricultural advisory, the first thing that we can note is that we have what we call the agricultural innovation systems. So in agricultural innovation system, we have a workflow where we have national agricultural research centers. They can be 5 or 10. They do research and advise agricultural training and education. From agricultural training and education, it informs agriculture extension. And then from agriculture extension, the information gets to the farmers. So this is the normal or the classical approach to agricultural advisory, or the way in which farmers get information. So we have these research centers across the country, and some of them are actually commodity based. One is for wheat, another for maize, another for coffee, and then they do research, and from their research they can advise agriculture extension workers, and also the research can inform training in education systems. So this is the classical approach, but in reality we actually have more actors who are influencing the farmer. So the information that the farmer has is not necessarily only coming from agriculture extension workers, but it's also coming from other sources like exporters, other farmers, producer organizations, NGOs, credit suppliers, and sometimes you don't even know where the information is coming from. That's why you see this blank arrow. The farmer just know to do something, but you can't know exactly where they got that particular information. So if you look at this chain, what are the skills or what are the issues the people who work in national agricultural research centers or agricultural extension or agricultural colleges, what information or skills do they have? Normally we talk about crop science and agronomy, entomology, plant pathology, soil science, biotechnology, and breeding, agricultural engineering, and agricultural economics. So if you look at this skill set, then comes the question, where do we get spatial models influencing agricultural advisory in this chain? So you find that maybe in soil science, they teach something about remote sensing. Maybe they teach something about GIS, but it's not always the case. Maybe in agricultural engineering, they can also teach GIS or a bit of geography or spatial modeling. But definitely we find a lag in terms of how spatial models influence this traditional way of doing things, basically, which I think we need to change. So from my personal experience, I've worked in national agricultural research systems where I did research in greenhouses or glass houses. So this is one of my experiments that I did to evaluate a new fertilizer product. And in 2 weeks, when I came for evaluation, I already had my results. So it didn't take long to know exactly what is the effect of the treatment effect. As you can see that some of the plants have already died. So this is the classical way. You have these research centers that are doing research, and then they give farmers different advisory based on their research. I also did another research, basically, which sought to look at does organic nutrient sources provide more resilience in terms of coffee. So I have these pots, and then I plant my coffee, and I have different treatments, the organic treatment, the integrated, and then the inorganic. So the integrated is a mix of the organic and integrated, basically. So from this pot experiment, and you can see this is in 2010, basically I still keep the photos from way back there. So what we basically find is that in terms of the height of the coffee plants, in the inorganic treatments, they tend to be taller, basically, than in the organic treatment. But in terms of water supply, because I also have 1,000 mils, 750, and 500 in terms of irrigation. So if you supply more water, your plants generally they also become taller compared to when they have less water. But the idea was then to look at the interactive effects of the water and the inorganic sources. So what you see here, first of all, is that if you have inorganic fertilizers and you have a lot of water, the 1,000 mils, you tend to have better plants. So inorganic fertilizers, they do well when you have more water supplies. But when the water levels are low, you find that the organic fertilizers, basically, they tend to perform well. So from this experiment, you see in the pots, this is how it evolves until I wrote this paper, which can actually inform the farmer that, okay, if a farmer uses organic fertilizers, they can actually get more resilient coffee systems compared to when they use inorganic fertilizers under climate change. So that's the advisory, which is based on a glasshouse experiment. We also have these field trials, so we can move the trial from the glasshouse to the field. And here we have examples of some coffee research that we have done on in the field, basically. And from the field, where I can show you one example, where we wanted to find out what is the best combination between coffee and bananas the farmers can use. So in the first treatment 1, we don't have any bananas. And treatment 2, we have 1 row of coffee in between 2 rows of bananas. And then we have 2 rows of coffee in between bananas, and then we have 3 rows of coffee in between bananas. So we want to see which of these actually performs the best in terms of growth, yield, and the economic performance. So the field trial from Google Earth basically looks like this, and we have a randomized complete block design, and you can see the arrangement of the different trials here. And then you can also, I also have some photos basically from the field, where you can actually see that here I have 1 row in between the coffee bananas, and here I have 2 rows, and then yeah, it's randomized across this landscape, and then I have the results basically. So what you see is that the leaf miner tends to prefer open areas. So when you have a lot of open coffee, you tend to have more infestation basically. So it's not a good idea to have the no banana intercropping, because pests become actually more. So we can basically use this in terms of advising the farmers in terms of the implications of what combination they can actually use for the farms. So the interesting part about this research is that apart from having it at the research center here, we also did this research with the different farmers on the landscape. And what we found is that on one farmer located here, the results, they matched exactly the same as the ones that we had at the research station. And at one farmer here, it was not so much. And at another farmer, it was completely different, where they actually got more yields in the open area compared to where they are actually intercropping. So the question is, if we are doing this kind of research station-based research, which are not spatial, how do we scale these to field trials, and how do we inform the farmers? And if we try to inform them using the same model, you find that we get different results because of different environments, different management systems, different soils, and different other factors, where the results that you get on the research station can actually be different from the ones that you get on the field trials. The same with the arrangements that the farmers have. So when I say you have 2 rows of coffee in between bananas and 3 rows, you find that the farmers, they also plant the bananas randomly. They don't do these rows that I'm talking about for some reason. So how can we directly translate the results that we get when I have rows to a farmer who doesn't use these kind of rows in the field, basically? So it's very difficult to upscale the individual research that we do at the station. And this is the reason why I believe we need spatial models that take into account the differences that we get across the landscapes in terms of the performance of these research results from stations. So this explains my drive or my interest in spatial modeling, so that we can be able to translate the results that we do at the research station across a bigger climatic environment. So there are different ways to do this. The first one is the pixel level studies, or we can also do this at administrative level, basically. So I'll talk about these two approaches, giving a bit of case studies of how you can do a pixel level spatial modeling study for agriculture, or do an administrative level study. So in the first case study, I want to talk about crop suitability modeling, which is the first aspect, basically. So when you talk about crop suitability, we are basically measuring how easy or how difficult it is for a certain area or a place to meet certain production targets. So is the climatic and other biophysical characteristics able to make a crop complete its crop cycle, which is from planting to harvesting? So the environmental factors, do they support this to happen, basically? So the principle is borrowed from ecology, basically, where people talk about the realized and fundamental niches. And in this particular case, we are applying this to a managed crop, basically. So you have an environmental variable plan where we say, if you increase any variable, it's not good, and if you reduce it too much, it's not good. So I'll take an example of temperature. If you increase temperature for crops beyond 35 degrees, then you start having heat stress. But if you reduce it too much, you then start having cold stress also, until you get to a point where the plants are not able to grow in the latency phase. The same applies for water supply. Either it's drought or it's hypoxia, where the roots are not able to respire. And in both cases, the plants will basically die. So in crop suitability modeling, what we are doing is that we are looking at the optimum areas where a crop can actually be grown. But for crops, we also know that we have the natural influence and then we have the management influence. But the assumption here is that the management influence comes only on top of the natural influence. So when you have management and technology, they can only work on top of the natural environmental suitability for a crop. So the natural factors, they remain important for the crops. Basically, so we have the natural influence, and then we have the management and the technology influence, basically. So you look for areas. This square, we are looking for it. Where can we get areas which meet the optimum requirements for a particular crop? And then you can get this from field studies, or you can get this from field samples that you use in the modeling process. So this is the scientific explanation of the process, while I exclude all the equations that are behind this diagram. So in other words, crop suitability models, it produces maps which are based on observed relationship between current production and environmental variables. So you're basically looking at the center part where management, precipitation, temperature, and topographic factors are sufficient to make sure that your crop grows well. And when we talk about this, like I'm saying, it's borrowed from ecology. The first thing that people talk about is that crops are managed. The people plant, and the people have a significant influence. I understand. That's why we also have a management module here to actually capture how human management influences this. But at the same time, if we had total human influence, then we would actually be growing coffee in the Antarctica, or would be growing cacao in Glasgow or in London, basically, which is not the case. Despite the advances in technology that we have, we still have production for different crops in different areas. So it basically means that the natural factors, they remain more important than the human factors. And yet we can still account for the human factor within the model. And then in climate change studies, we look at the current suitability, and then we also change the variables and put the future projected variables so we can get an idea of how the future suitability will be. And the difference between the future and the current gives us an idea about the impact of climate change on that particular crop suitability. So that's the basic principle. So now I want to show you how we apply this crop suitability modeling in agricultural decision making, basically. So we use this crop suitability modeling to look at the impacts of climate change on agroclimatic suitability of major food crops and crop diversification potential in Ghana. I'm happy that in the audience there's someone who is actually in Ghana, so that's a plus in terms of the discussion and also in terms of the context of this study. So the idea is that crop diversification, it has been talked about a lot as a strategy for climate change in terms of enhancing agricultural resilience. And when we talk about crop diversification, we are looking at the farmer being able to grow 2 or more crops on their piece of land. And when we say 2 or more crops, then we then talk about how is this achieved. The first one is that we can have what we call the concurrent suitability. When we talk about concurrent suitability, is that within the farming season, the farmer is growing the 2 crops. So either they are growing groundnuts and they are also growing maize, or they are growing cassava and then they are growing also another crop during the same growing season. It's just a way in which they arrange their fields. But we can also have what we call sequential suitability. Sequential suitability is when a farmer in a particular season grows another crop, and then in the next season they grow another crop. So they, for the first 3 months, they grow maize, and then after that they grow another crop within the year. So both cases is crop diversification, but much of the focus here is on concurrent suitability, because I think it's more common for farmers to actually have more crops during the same growing season than to have crop sequential suitability, especially in rain-fed agricultural systems. And when I talk about diversification, a lot of people kind of have a misconception that diversification is equal to intercropping, which is not the case. Intercropping is part of cropping diversification, but you can also have diversification where the farmer allocates different fields to different crops. We also consider that crop diversification, which is the main focus of our approach here, because we believe that it's more common for farmers to actually have different fields, having different crops, than having them intercropping, although intercropping is important. But when you look at diversification, there are no quantitative assessments of which crops can do well together and on how climate change can affect these crop mixes. So the idea was to fill this gap and provide quantitative assessments of the impacts of climate change on crop diversification potential using Ghana as a case study. So we got agricultural production data set from the Ministry of Agriculture in Ghana from 2006 to 2016. So what you see in the first plot is basically the trends in agricultural production for the 4 crops. And take note that cassava is on the right axis because it has these large values. So what we did next is that we divide the crop yield into 4 classes. We have what we call the optimal, based on the 75th percentile, and then we have the moderate from the 5th to the 75th percentile, and then we have the marginal from the 25th to the 5th percentile, and then we have the limited, which is the yields that are less than 25th percentile from the first graph. So we have 4 classes of crop potential already in the first place. And then we have these bioclimatic variables, 8 variables that are related to the production system or the growing system in Ghana. And then we also have soil factor, the topsoil organic carbon, to influence the production system, because it's not just the climate factors, but also the soils. They are very important. And then we use the CHIPS climate data to fit the model and the WAF day temperature data set. And then for future climate, we use 4 GCMs, the IPSL, the HardGem, the MyRock, and I forgot the last one. And then from there, we put this into the extreme gradient boosting algorithm so that we can be able to train the model to learn from the current yield levels so that we can be able to make the spatial projections. I can talk all day about how the extreme gradient boosting algorithm works, because that's so common with people from remote sensing. They love their methods, but for today, I will just say I use the XBoost. So from there, from the fitting the models, we evaluate the accuracy, how good is the model fit, and then so that we can have confidence in terms of using it for the different crops. So for all the crops, we find that the accuracy was 75% and above, which was good. Basically, and our AUC in all cases was also above 0.81. So we get some confidence in terms of how we can use this. So having gotten some confidence, we also get information about the importance of all the variables. So which factors are important in driving the suitability for the different crops. Basically, what you see is that precipitation is important across the 4 crops, but for sorghum, it's slightly less compared to when you compare the importance of precipitation for maize, groundnuts, and cassava. And also interesting is that if you look at temperature variables, they tend to be more important for sorghum distributions, which also goes with the non-ecology or physiological characteristics of sorghum production, and also the areas where it is actually produced in the country. So we get an idea of, or to explain the distribution that we get. And then we get the spatial distribution in terms of suitability for the current climate, for RCP 2.6 and also for RCP 8.5. So we can tell how is the suitability going to change between the different crops over time. So you can just look at a few examples, because it's like a big map. How is it changing basically for maize from the current to RCP 2.6? How is it changing from the map in terms of sorghum? How is it changing for cassava? So what you find is that there's a positive response in terms of groundnuts under climate change, but the other crops, maize, sorghum, and cassava, they are going to become less suitable, basically, because the optimum areas are going to become much less. This is what we see here in the optimal areas. For maize, for sorghum, and for cassava, they are going to become much less, but for groundnuts, there's also a chance that under RCP 8.5, groundnuts can become more suitable in Ghana. And then we can also get the qualitative results at national level, basically. How is this going to change in terms of percentages suitability, which we can use for the planning purposes. So when I talk about this, I'm looking at this as individual crop suitability, but my interest is actually in crop diversification, where I'm saying, how is climate change going to change the ability of a farmer to produce 2 or more of these crops? That's where the actual question is. So to do this, I have these 4 classes: the marginal, the limited, the moderate, and then the optimal. So from the optimal, I can then combine my individual crop maps, and I can use addition. So since I have 4 crops, and if I add them together, I get values between 4 and 16, because if it's 1 plus 1 plus 1 gives me 4, which is the least suitable. And then for the most suitable, in case I have where it's optimal for all the 4 crops, I expect to get a value of 16. So I get 12 values, which shows suitability for the different crops, which I can then also convert to a map. So from here, you can actually see the areas where you are more able to grow more crops compared to just producing 1 crop. So the bright colors, they show you the areas where there is less potential for growing more crops, and the green, dark green areas, they show the areas where you are actually able to grow more crops. So in other words, we are saying we can identify areas where crop diversification is more likely to be possible compared to where it is less likely to be possible. And under current and also future climate conditions. Our reference period in this case was 2050, which is 2045 to 2055 period. So you can actually see how is climate change going to impact crop diversification potential. So for example, if you look at the Upper West region, we have a lot of green areas under current climate conditions, which means we are able to grow more crops. But under RCP 2.6, they become lighter. And under RCP 8.5, they become even worse in terms of suitability for growing multiple crops. So the farmers will not be able to grow multiple crops under climate change in this particular case. Basically, we can also get the values or the figures in terms of how the suitability is changing. And like I was saying earlier on, the potential for growing more crops under climate change basically will be going down. And so the multiple crop suitability, it increases the diversification potential under current and also under future climate conditions. So what we find in this study is that the areas where the farmers are able to grow 2 crops is the highest in terms of percentages. So we want to determine of these 2 crops, which are they, and how is the potential for these 2 crops likely to change under current and future conditions as well. So we go back and then I add my maps. So if I'm adding 2 maps, the list is 1, and if I add it, it basically means I get 2, or the highest is 4. If I add it, I get 8. So I get an idea, or in terms of values between 2 and 8, in terms of potential impact of climate change for dual crop suitability. And I can do the same across the period and produce this map for the different crop combinations: maize and sorghum, cassava and sorghum, groundnut and cassava, maize and cassava, across the whole country, so that I can advise that the farmers that in this particular area, you have more chances of growing maize and cassava than you have for growing sorghum and groundnuts, so that the farmers can adopt the technologies that are suited for that particular area. You can also extract the information and get the percentages in terms of the dual crop suitability that you can basically use. So from here, my understanding of diversification, like I said, is in terms of ability of a farmer to produce 2 or more crops, which you can get from the suitability models. And you can also look at how the farmers can also intercrop, because for them to intercrop both crops, they need to be suitable in that particular area. That's the general understanding. But in a certain way, my other understanding of crop diversification is looking at the farmer's plate. This is one of my favorite meals from Ghana, which is called tozafi. And what you see from here is that you have maize as the main staple, and then we also have groundnut soup. So for you to produce this meal, you need to have suitability for the maize and suitability for the groundnut also. So studies in terms of diversification, they should also, when we talk about food security, we should not just talk about cereals, because then the farmers are not just eating the maize alone, but they need this kind of crop combination. So we also need to imagine the final outcome, basically. So from the map, we can see where is this favorite meal most likely to be produced in Ghana by looking at the combinations of maize and groundnuts, so that they can do the groundnut soup and the maize together. So that's the kind of overall implication. So what we find in terms of key conclusion from this study is that we can understand the biophysical predictors of suitability, which also correspond to what we know about crop requirements. And for the 4 crops, groundnuts, they are the most resilient under climate change. They will have slightly less impact, basically. And you can also find that climate change impacts, they are site and crop specific, which goes back to my earlier question that if you do a study at a research station about the climate impacts, you don't capture the heterogeneity in climate response across the landscape, basically. And we project a reduction in possibility for crop diversification in Ghana under climate changes. So we can capture the possibilities, basically, across the whole landscape in terms of crop suitability. But we also know that there are some weaknesses in this kind of approaches. First of all, the quality of the data set that we input into this model also affects the outcomes. And then we also have using different GCMs, which have different projections in terms of climate response. And then we also have this different, one is showing a wetter future, another is showing dry future. And then we are looking at the average. And because of the resolution of the modeling, we also include other lands which may not be available for agricultural production. So when I say 5% or 12%, they need to look into consideration that it's not all the area that it would be available for agricultural production. And this modeling also omits the direct physiological interaction in terms of multiple cropping. Because when you have a farmer producing different crops, there are interactions that take place within the crops, basically. Nitrogen fixation, water retention, pollination also happens, basically. So we don't capture that in this kind of suitability modeling, basically. So we have to consider that in interpretation of the results. And because of these weaknesses, we only consider that we should look at the relative changes rather than the absolute changes in terms of suitability for the crops. So if you do individual study, you get the impacts, yes. But if you do a spatial modeling study, you also get results in terms of how the environment will be suitable across the landscape for different aspects, which you can use for agricultural advisory, better than a study that is based on research station. Not saying that studies from research stations are not important, before I offend some people who are working on that. So from here, I want to take a small coffee break and ask if there is any one question of understanding before I do the last part, which is the shorter part for administrative level spatial models.